today's topics are going to be the truth table, Boolean algebra, where we'll be talking about the operators, postulates, how we simplify a Boolean algebra. Also, we'll be looking at the logic gates. Then we'll talk about the K-maps or the Carnot maps, which helps us to simplify the Boolean expression in a much easier manner, instead of just applying the postulates in order to simplify a given expression. Then we'll talk a little about the Venn diagrams. And lastly, I'm going to give you guys a set of questions for homework, and just to brush up the concept that we'll be studying today. And then we'll discuss those questions tomorrow again. So starting with truth tables, this is a logical table used in mathematics as well as computers. It's mainly helpful with Boolean algebra. We use this table in order to decide whether a compounded statement or a complicated statement is true or false based on its components, truth or falsity. So for example, in this particular table, we suppose have two variables, x and y, and we want to have we have a compound statement, say x dot y. So here, x basically can take two values, 0 or 1, so as y. And since we have two variables, we have a total combination of 4. And x dot y basically gives us whether the compound statement is true or false based on the based off of the components and what's the value for those components. Now, Boolean algebra. So this is algebra of logic, which aims at analysis and design of logic circuits. Statements which can either be true or false are called logical statements. For example, he is wise. So we can say that this is a logical statement because it can either be true or false for someone. Here, 0 and 1 do not contain any arithmetic significance, but only have a logical significance. So 0 means false and 1 means true. And since these are just constants, so we call them Boolean constants. Now we have three main Boolean operators. The first one is AND, the second is OR, and the third one is NOT. So let's take a closer look at AND. Suppose we have two statements, X, which denotes he is tall, and Y denotes he is wise. So the compound statement, he is tall and he is wise, can be written symbolically as X and Y, or X dot Y. Dot basically is used to represent the operator AND. So let us list all the possible combinations of X and Y. It's the exact same table that we saw in a couple of slides ago. It's where we have two variables, X, Y. They have their own values, and then we have the values for the compounded statement X dot Y. Here you will notice that X dot Y is only true if and only if X and Y are both 1. Is it clear so far? Or does anyone have any questions? Okay, so now the next operator is the OR operator. So we're going to take a look at the same compound statement, he is tall or he is wise, which can be represented symbolically as X or Y, or we can also write it as X plus Y. Here, the plus sign is used to represent the OR operator. The truth table for the OR table is same. We have the 0 and 1 values listed in a column format for X and Y, and then we make a column for X plus Y where we have 0, 1, 1, 1. That is basically X or Y is true if either of X or Y are true or both of them are true. So this is where we have the least satisfy condition, where either of the variables needs to be true, and there's no hard and fast rule that only the compound statement is going to be true only when both of the sub-statements are true. Now the third operator is NOT. So let us take a look at this statement X, which denotes he is wise, and let us say it's any statement. Then not X or exclamation X basically means he is not wise. This does not mean he is stupid or foolish. It just means that we've negated the original statement. And the truth table is, so X basically will have two values, 0 or 1. And the negated X is going to have 1 or 0. So from the truth table, it is clear that X double bar is basically equal to X. So moving on, so now we're going to take a look at Boolean postulates. So here we have two columns. Let's take a closer look at column 1. Here we're going to be using the AND operator. So the first one is 0 and 0. That's going to give us 0. Then we have 0 and 1. That's again going to give us 0. Then we have 1 and 0. That's again 0. And then we finally have 1 and 1. That's going to give us 1. It's the same thing that we saw 2 slides ago, where we were looking at the truth table for the AND operator. So now take a look at column 2, where we basically switched the zeros with ones, and we changed the dot operator with the plus operator. Basically, we swapped the AND operator with the OR operators, and we changed zeros with ones. Since we did this interchanging between zeros and ones and the pluses and dots, such expressions which are obtained by making these interchanges are called duals. So it's pretty much it's pretty straightforward. So if you change a 0 with 1 or dot with plus, you'll get a dual. But if you change 1 or plus to 0 and dot, it's going to give us the vice versa case. Now here are the main theorems that are important for Boolean algebra. These are mainly used to simplify the given Boolean expression. And each of the expressions can be verified using the truth table. So here we have 0.x, which gives us 0. So whenever you take a statement and multiply, say this statement and false, it means that you're going to always take the false value. Or else when so basically whenever you're using false and operator together in a compound statement, then the result of the compound statement is always going to be false. And whenever you're taking an AND operator and the value 1, or basically the value true, then you're always going to get the X or the variable part of the statement. So for example, 1 and X is always going to give you X. If we take a look at the dual form, then we have 1 plus X, which is always going to give us 1, because true or a particular statement, then we're always going to get the particular statement because we're just keeping the true version as it is. And when we have 0 plus X, we're always going to get X, though there might be some arithmetic significance that might be visible here, but it's always going to be the logical significance that we're going to take care of in the Boolean algebra. Does anyone have any questions regarding those two things that I just talked about? Okay. So now moving on to the next laws. So first one is idempotent law, where we have X and X. It's going to give us X. Similarly, X plus X is going to give us X. Then we have the commutative law, distributive law, associative law. Those are pretty straightforward because we've also used them in mathematics as well. Then we have these 3 laws, the 3 absorption laws. These come pretty handy when you're given a particular complex Boolean expression and you want to simplify them in order to get the least number of variables. So it is highly recommended to make sure that you have these 3 laws in mind whenever you're trying to simplify a Boolean expression. Then we have the De Morgan's law. As we all know, it's very useful in mathematics as well. So with the similar importance, it is very helpful when we are trying to simplify the Boolean expressions. So here's the verification of one of the theorems that we just saw on the previous slide. So here we're trying to prove whether the distributive law actually holds for Boolean expressions. So I created this truth table where we have the three variables x, y, z, and then I wrote the combinations x plus y plus z, x, y. Then I have x and z, and then I have x times or x and y plus z. And then ultimately I have the right hand side of the expression, which is xy plus xz. If you take a look, then we have the rightmost columns have the same exact values. So this means that we can actually verify distribute any kind of laws using the truth tables. So now we're going to see how we can simplify Boolean expressions. So there are two ways of doing that. So the first one is sum of products. These are expressions in which all the variables are connected with AND operator. So the variables are connected with AND operator in each term, and all the terms are connected with an OR operator. Each term of the SOP is called a minterm. And this product is basically denoted by this sum is basically denoted by a summation sign or a sigma sign. So in order to, like, if you want to remember how which Greek letter denotes which type of expression, then SOP starts with S, same as sigma. So you can just say that sigma stands for SOP. Now let's take a look at POS, which is product of sums. These are expressions in which all the variables are connected with OR operator in each term, and all terms are connected with AND operator. In this, each term of POS is called a max term. And ultimately, this product is denoted by pi. Similarly, in a similar fashion, how I told you guys to like memorize how which symbol signifies which expression. Here, POS starts with P and same as pi. So that's a way to like remember it if you ever get confused. Then one thing to note is that dual of minterm is max term and vice versa. So basically, the dual of SOP is going to be the POS of the given expression. So now let's take a look at this example where we have x bar y or x not y, which is not a SOP form because variable z is missing from the product. So, so in order to convert this expression to a SOP form, we multiply the term z plus not z, which is equal to 1. So if you want to verify how is this possible, then what you can just do is that since we know that each variable consists of, will always have two Boolean values or two Boolean constants, it's going to be 0 and 1. So whenever you say, for example, so let's say z is equal to 0, then not z is going to be 1. So 0 plus 1 is going to give me 1. On the other hand, if I would say z is equal to 1, then not z is equal to 0. So 1 plus 0 is again going to be 1. So ultimately, we got this function where we have x bar yz plus x bar y z bar. So now both terms have min terms, and f is in the SOP form. Any questions on this? And please let me know if you would want me to like slow my pace, because I don't want anyone like not understanding something that I'm saying. Okay, so now we're going to talk about Boolean algebra in computers. So logic gates are fundamental building blocks. These are circuits that combine input logic variables to produce some output logic variables. The three main fundamental logic gates are NOT, AND, and OR. These are the exact same Boolean operators that we just talked about. Here's the symbol representation or the logic gate for each of the operators. So the triangle with the circle is going to be the NOT operator. Then we have this symbol which denotes AND, and then we have this curved one, which basically denotes the OR operator or the OR gate. Here's the table which basically shows you the truth table, the symbols for each of the operators. Then we have the block diagram for each of the operators. And this basically explains what each of the gates does. So the first one negates the input. The second one is always going to return you 1 if and only if both the inputs are non-zeros. And the third one is going to be always 1, even if one of the inputs is a 0. Clear so far? Okay. So here are some more complex gates that come handy during the exam. So the first one is the NAND gate. It's basically not AND here, or if you take a look at the truth table for AND, we have the Z column to be 3 zeros and a 1. The values for not AND are going to be just the opposite, as if I applied the NOT gate on a NOT operator on AND. So I got 3 ones and a 0. The way it is denoted in a symbolic form is the upward arrow. A block diagram is going to be the same symbol that we use for AND, except we just add on a small circle ahead. And this means that this gate is always giving me an output of 0 if all the inputs are 1. Now we have NOR, which is basically not OR. Here it's the exact, it negates the results for the OR gate. So here we have just 1, 1, and we have 3 zeros. The way it's symbolically represented is in the form of a downward arrow. It's the same OR gate in addition to a small circle on the right. And this means that it's going to give me 1 if all the inputs are 0. Then we have these two more complicated gates. So the first one is XOR, that's exclusive OR. What happens here is that whenever the inputs are different, then only you're going to get a 1. But whenever the inputs are both same, then you're going to get a 0 always. So let's take a closer look. So here we have X and Y. Since both of them are 0, so that is why we got the compounded statement as 0. But in the second column, suppose X is 0 and Y is 1, then the compounded result is 1. The way we represent this in a block diagram is using an OR gate, but we just add a curved line on the left side. And then the last gate is X NOR. This is similar to how we looked at NAND and NOR. Here it means exclusive not OR. We basically negate the results of the XOR. So here, if you take a look at this column and this column, it's basically just the negation of the above column. So here, what it means is that whenever the inputs are the same, then only you're going to get a 1. Else, you're always going to get a 0. Is this clear? Okay, let's move ahead. So here are like 2 examples of some random circuits. So this is how like the circuits are going to be given on the exam. So for example, I have this circuit, and so one of the examples could be, tell me the final expression for this given circuit diagram. Similarly, in this part, it's the same thing. I'm given a circuit, and I want to come up with the expression that is represented in this particular circuit diagram. One thing to note here is that in XOR, we basically use the plus sign with the circle, right? So in the first diagram, what it does is that we are basically showing a logic gate circuit diagram for the XOR logic gate. So here, if we have 2 variables A and B, and if we apply an XOR gate on these 2 variables, then this is the simplified expression that we get, which is A B bar plus A bar B. So that's how you can basically use it in like Boolean in expression simplification if you ever encounter a question where you're given A XOR B. So now I would like to give you these two circuit diagrams and would ask you to give me the resulting expression for these two circuit diagrams. And you can put your answers in the chat box. Also, if you want to represent A naught, you can just say A and quotation mark. That's another representation of a negated A. Okay, these looks good. So these are pretty much the expression that almost everyone wrote down in the chat box. So very good. Even though these diagrams were very simple and easy, however, the questions that I put on the practice exercises and the ones that we're going to be discussing over the course of the other lectures are going to be a bit harder. So now let's talk about Carnot maps or K-maps. These provide a pictorial method of grouping together expressions with common factors or logical variables, and therefore helps in eliminating unwanted factors or logical variables from the expression. These are basically a much easier way of removing unwanted variables from the given expression in order to simplify the overall expression, instead of applying different Boolean postulates and try to do all sorts of Boolean algebra. So a K-map can also be described as a special arrangement of the truth table. On the right, we have shown a two variable truth table and how a K-map would look like for those two variables. So here we represent one side with A and the other side is represented with B. And each of the columns have a Boolean constant. So the first one is 0 and the second one is 1. Similarly, the first row is going to have 0, the second row is going to have 1. Ultimately, each of these cells are going to represent a particular number based on how you convert the cells using Boolean binary numbers, and ultimately you can just convert them into decimal system. So for example, the first cell is going to be 0, 0, so that's just going to be 0 in the decimal system. Second one is going to be 0, 1 in the binary number system, but if I want to convert it into decimal system, it's going to be 1. Then we have 1, 0 in this third cell where we have C. This is going to be representing the number 2. Because that's how you convert a binary number into decimal. And then in the fourth cell, which is represented with D, you're going to have 1, 1, which is basically number 3. So that's how you could number all these cells. And because at times there are going to be questions in which you're just going to be given expressions like give me a SOP form and the given cell, the cells that you can use are sigma 2, 3, 4, 5. And since we have 5 in that, we're going to be using 3 variables. And then accordingly, you're just going to be given numbers, and which becomes very easy when you know how to number each of the cells in a K-map. So here are the examples of 2 inputs, 3 inputs, and 4 inputs. These are mostly what we're going to be using on the exercises, as well as these are mostly prominent on the exam as well. So you most likely will be looking at a lot of questions based on 3 inputs and 4 inputs. It's very unlikely you'll get any questions on the 2 inputs because it's very easy. So let's take a closer look at 3 inputs. So here we have ABC. So on one side we write AB, and the other side we write C. So here the number of rows is just going to be 2, because each variable has only 2 Boolean values or Boolean constant, that is 0 and 1. However, since we're using AB on the top side, so that is why we have 4 columns. Now we're going to always start with 0, 0, and we go up to 1, 0. So basically how you numbered the columns is 0, 0, 0, 1, 1, 1, and 1, 0. And then since we're only using 1 variable on the bottom side, so it's very easy to just write 0 and 1 on the rows. Here you would notice that I wrote these numbers in the binary number system. So these binary number systems, when converted into the decimal system, each of the cells are going to be represented with a number. So for example, this is going to be 0. This is going to be 1. Then this is going to be 0, 1, 1. So it's going to be representing number 3. Then we have 0, 1, 0. So that's going to be 2. So always make sure that whenever you're writing columns, or whenever you're writing the numbers on basically annotating each of the columns and rows, you are doing it in the right manner, because it's important to make sure that we have 1, 1 come before 1, 0. Similarly, if we take a look at 4 inputs, then we have 1, 1 as the 3rd row and 1, 0 as the 4th row, similar to how we had 1, 1 as the 3rd column and 1, 0 as the 4th column. So these second diagrams basically show which cell is denoted by which number. So here it's 0, 1, 2, and then 3. Then we have 4, 5, 6 is in the 4th column, and then we have 7. Then you would notice that because of this 1, 1 in the 3rd row, we basically have the 12, 13, 14, and 15 numbered cells in the 3rd row, because however, it would be more easy. It would be easier and more logical to have these numbers in the 4th row, because they're anyways bigger than the 4th row. But since it's based on like these, how we annotate the rows and columns, so that is why we have 12, 13, 15, and 14 in the 3rd row instead of having them in the 4th row. Any questions on this? Okay. So here we're just discussing the steps that we require for K-maps. So first of all, K-maps helps in finding Boolean expressions with minimum number of variables, similar to what I said in the first slide of K-maps. So Boolean expressions of 3 or 4 variables can be reduced easily without using any of the Boolean algebra theorems. Then K-map can take 2 forms. First form is SOP, that's sum of products, and the second one is POS, that's product of sums. Based on what it described in the problem. So for example, if you have a question which is using the sigma notation, then it's asking you to use K-maps and find the sum of products. But if there's another question which is which provides you with the values with a pi notation, then it's asking you to find the product of sums. So there are like 2 different approaches when you're trying to find the sum of products and the product of sums. They're pretty much similar. It's just that it differs on after the 3rd step. So so now let's take a look at the steps that are involved in solving expressions using K-maps. So the first one is select appropriate K-map according to the number of variables. This is based on the number of variables that we are given in the question. So it could be either 2 inputs, 3 inputs, 4 inputs. Then once you've decided which K-map is required based on the number of variables, then we're going to identify the min terms of max terms as given in the problem. So it basically means, so for example, if I give you summation 2, 3, 4, 5, so those are basically min terms, because min terms means SOP, and it's also evident because of the sigma sign. So what second step means is that identify which of the cells are going to be needed for this particular expression. And then for the max term, it's going to be pi notation, and then you will be given some numbers. Then the third step is for SOP, or the summation sign or sigma sign, put ones in the blocks of K-map respective to the min terms. And you can just fill out other cells with zeros, or you can also leave them as empty. The fourth is for POS, which is denoted by pi, you need to put zeros in the blocks of K-map respective to the max terms. And you can similarly put ones in the remaining cells, or you can just leave them empty. And then try to make rectangular groups containing total terms in power of 2, like 2, 4, 8. And once you've made all the, once you've grouped all the cells based on like how big you can make the rectangular groups, then only try to use squares or groups of 1. But the first priority is to group together as many cells as we can in a bigger rectangular box. And from the groups made in step 5, find the product terms and sum them up for the SOP form. Any questions on the steps? Okay, so here are some examples of K-map problems. So the first one is, for example, we're given some numbers. And so in the first one, we're basically trying to find a SOP for a given expression. So here we basically denoted all the boxes that were needed with ones, and we're trying to come up with the biggest box first, and then we're trying to group the smaller ones. So since these 4 cells are in close vicinity and helps us make a rectangle with 4 cells. So we first encapsulate all these ones into one particular rectangle. And then since we have this one remaining one, which is in the 4th column and 1st row, but it's always preferred to, like, you can always have like a repeated term instead of like having one term with more variables. So the preference is to have least variables with more terms. Sorry. The preference is to have least variables in a particular term. So here, since we already used this one, which is in 3rd column and 1st row, we are basically grouping it together with the one placed in 4th column and 1st row in order to make a box that is of 2 cells. So once we have that, then we come up with this expression. And the way we do that is basically, so in this part, in this box of 4, we basically see that which ones are the commons here. So here we see that Z is common. And on the row side, since X, both values of X are being used, so that is why this box of 4 cells is just represented using Z variable. So that's how we came up with this Z. And then when we want to represent this 2-cell box, then we know that it's denoted by X dash. And looking at the 2 columns that are 3rd column and 4th column, the common variable here is Y. So that is how we came up with the first term, that is X naught Y. Then let's take a look at second example. It's the same thing. Here we first boxed together the most number of ones that we could, which are in close vicinity. So here we created a four-celled box. Then we created a two-cell box. Here in the second column, we again used a common from the second row and created a two-box rectangle. And finally, in the fourth cell, in the fourth row, you would see that we created a two-celled box. Here, the one thing to note about K-match is that it's always cyclic. So this edge is basically connected with this edge, and this edge is connected with the top edge. So that is why we could basically club together the one placed in the first row and the one placed in the last row. And then let's take a look at this third example where we basically have all the zeros. This example, since we are using zeros in here, and we used we populated all the remaining cells with ones, and we box together zeros. So it means that we are working with a product of some expression. So here we created a box of 4, and then similar to what we looked at, saw in the previous example, we can basically form circles in a cyclic manner. So the columns in the first row and the two columns, the second column and the third column from first row can be clubbed together with the second column and third column of the fourth row. Any questions on any of these examples?
Sir?
Mm-hmm.
Sir, in example 1, hello, am I audible?
Yeah. Go ahead. Yes.
Sir, in example 1, like they have taken YZ as combination and XS separately. If I take XY with combination and ZS separately, will it make a difference?
It won't make a difference.
Okay, sir.
Yeah, you can do that either way. Any other questions? I'm going to take that as a no. Moving on. So now we're going to talk about Venn diagrams. So it's a graphical illustration of various operations and relations in set theory. A set S is a collection of elements that are members of S. And for us, this would be a collection of Boolean variables or constants. And elements of set are represented by area enclosed by a contour, or which is usually a circle. So here, for example, we have constant Boolean constant 1. So it's just going to be just the entire gray area. Then we have Boolean constant 0. It's going to be the entire area, a white area. Then we have, suppose we have variable x. As we all know that there are like two constant values for x, which is 0 and 1. So the one area is going to be enclosed in a circle and grayed out, while the 0 area is going to be just the entire white area. Then we have x naught. Here we're going to take since we're working with x naught, so now the x naught or the 0 value is going to be constrained into a circle, while the remaining area is going to be grayed out, which is going to represent the value 1 for the variable x. Then we have, so for example, we have two variables x and y. Then we're going to have two circles, and based on the operator that's been used between them, we will be deciding which area is going to be grayed out. So for example, in part E, x and y basically means we take an intersection of x and y. So that is why we have the common area of x and y grayed out, while the rest of the entire diagram is white. In part F, we are taking we're using x plus y, which is the x circle and y circle, and we're taking a union of both of them. So the entire circular diagram is grayed out. Then we have x and y naught. Here, we're just going to take the exclusive x part, which is not common with y. So that is why the common part is also white instead of grayed out. And lastly, we have x, y plus z. Here we say that x and y. So we take the intersection of x and y. So that is why we have the grayed out section between x and y. And since we're taking a union with X and Y of Z, so that is why we have the entire circle of Z grayed out. Any questions on this part? Okay, sounds good. And with that, these are all the topics that I wanted to cover today. We've covered mostly all of the Boolean algebra, including Venn diagrams and K-maps. Now I have a set of questions for you guys that I wanted you guys to practice. So what I'm going to do is that I'm going to share this link in chat, and I will be keeping this form open until I think it's 7:30 there. So let's just keep I'm going to keep this form open till 8 a.m. Indian time. And I'd like you guys to take a look at these questions and